Okay, welcome to online lab number 6. This is the lab on static fluid pressure and fluid flow. This is a topic we cover in Physics 101. I don't know that 201 covers this, but it's an important topic and it's something that we don't usually get to do in the lab. It's just difficult to do experiments with fluid flow and fluid pressure. So we're really excited to be able to do this in an online area. Several big ideas that you need to understand. The first is that of atmospheric pressure. And atmospheric pressure is the pressure due to the atmosphere that sits above you. So if you imagine if this is the surface of the Earth right here, there is an atmosphere. Let's just say that the atmosphere has a distinct boundary. There's an atmosphere that is over the surface of the Earth. And if you can imagine, then if you're at a point right here, there's an entire column of gas that sits on top of that point. And so down here, if you have a person, for example, they will experience the full weight of this column of gas that sits on top of their head. And this actually causes an immense pressure, which is the atmospheric pressure, and the pressure due to the atmosphere at sea level, where this column of gas is at its largest value, that it's at its tallest, that you have the most gas on top of you at sea level, the pressure at sea level is approximately 1 times 10 to the 5th newtons per square meter. That's how we measure pressure. In fact, pressure, more broadly defined, is equal to a force per unit area. And so force, which of course is measured in newtons, and area in square meters gives us our SI units for pressure. Another pressure that you'll often commonly see is 1 atmosphere. 1 atmosphere is equivalent to 1 times 10 to the 5th newtons per square meter. And then we have another special unit for this. A newton per square meter is equivalent to a pascal. So 1 newton per square meter is also called a pascal, after the scientist, philosopher Pascal, Blaise Pascal. Uh, and so when you abbreviate the Pascal, it's going to be an uppercase P, and actually we usually label it the units as a PA for pascals. So that is atmospheric pressure. Now when we're measuring pressure, we'll use some sort of gauge. And when you're using a gauge, it's important to understand the difference between gauge pressure and absolute pressure. So we have two different pressures, the gauge and the absolute pressure. My dad worked at a tire shop when I was a kid, and people would come in, and I worked there with them, and they would always say, check the pressure in my tire. And if you think about a tire, it has a certain pressure of gas inside of there, and you would have this little, valve, and you would go and you'd measure, and you would find that the pressure is equal to something like, I don't know, 35 pounds per square inch. Of course, that's in the metric system or in the British system. But in reality, the pressure inside of that tire is much, much higher than 35 pounds per square inch. Because in reality, we have the atmospheric pressure, which already exists. Then the tire is actually just 35 psi above the atmospheric pressure. So absolute pressure is always bigger than gauge pressure because absolute pressure will include the atmospheric pressure. The relationship between these two, the absolute pressure, I'll call it PABS, is going to be equal to the gauge pressure, I'll just call that GA, plus whatever the atmospheric pressure is. So the absolute pressure is the gauge pressure plus the atmospheric pressure. So for example, if I'm reading, I don't know, 200 pascals on my gauge pressure, that would be my gauge pressure. But in reality, my absolute pressure is going to be equal to that 200 pascals plus my atmospheric pressure, which is approximately 100,000 pascals. And so the absolute pressure would be 100,200 pascals. You'll find actually in your simulation that the atmospheric pressure isn't exactly 100,000. You'll find that it's either a little bit above or a little bit below that. Another part of the lab is you'll be measuring the pressure due to a height of a column of fluid. And as I define fluid, first of all, let's just say fluid is any material that flows. Which of course includes both gases and liquids. So I have the pressure due to the atmosphere, which is a gas, but I can also have the pressure due to water, for example. So let's imagine that I have a container of water and I have a point down here, and I want to know what is the pressure equal to at that depth. I'm going to say that this is a depth H. Now, first of all, I know that there is a pressure up here. This is the pressure due to the atmosphere. Sometimes we call this P naught, and this is equal to 1 atmosphere, or 1 times 10 to the 5th pascals. Now, if I imagine down here that I have a surface, a cube, imagine that's a cube, there is a column of water that sits on top of that cube. And let's say that one face of this cube, this top face, has an area A. So the pressure at that point would be equal to the force weight of the water that sits on top of that cube divided by the area. The force weight is going to be equal to the mass of the water. That is the mass of this column of water times acceleration due to gravity divided by A. Now, the mass of that is going to be related to the density. Remember that density is equal to mass divided by volume. So if I wanted to find the mass, it would be equal to the density of that material times the volume. So whatever the volume of this column is, if I multiply that times the density, then I have the mass of that column. We did this in the in-class lab where we explored the relationships between density, mass, and volume. So I can get then an expression for pressure by putting in this for mass. I get rho Vg divided by the area. However, recognize that V divided by A, the volume divided by the area. In general, I can say that the volume is area times the height of the column. Imagine if you have a cylinder like this. I have a certain area right here and a certain height. The volume of that cylinder is equal to the cross-sectional area, that's the area of the circle on the top of the cylinder, multiplied times the height. In general, that expression is true for any symmetrical object, that the volume is equal to the area of the end times the height or length of that material. So I divide this by A, and now recognize that these two A's will cancel out. And just leave me with the height. So here, where I have V divided by A, I can replace that and get my final expression for pressure, which is going to be rho times G times H. But also recognize, as I said here in the beginning, that we also have this pressure at the top. So it's sort of like this right here would be like our gauge pressure. But then we also have to include our atmospheric pressure to get the absolute pressure at this point right here. So my absolute pressure at this point would be equal to rho GH plus P naught. Now, let's go on to flow rate. Flow rate is kind of important. Imagine that if I have a pipe and I have an ideal fluid, as we'll see in class, is, hold on, I'm sorry, I need to pause. So if I have an ideal fluid, and an ideal fluid will have 4 properties, we'll talk about these in the class in Physics 101, but they are non-viscous. So like water is not very viscous, but maple syrup, on the other hand, is very viscous. They are incompressible. All gases are compressible. So basically this leaves us just with, not fluids, I'm sorry, with liquids. Because all gases are compressible, liquids are not compressible. And then they have steady motion. That just means that at a particular point, the velocity, the pressure, and the density do not change with time. So steady motion is at a particular point, the velocity, the pressure, and the density are constant. Now, it doesn't mean that they can't be different at a different point. So the velocity and the pressure and the density might be different over here. Although actually, since it's incompressible, the density will always be constant because it's an incompressible material. And then finally, irrotational. I don't mean to be crass, but your toilet is a great example of a fluid that is not irrotational. It rotates a lot, actually. So we're assuming that the fluid is moving in a straight line. Okay, so we have two different flow rates. Mass flow rate. These are flow rates that are relevant when we're talking about the flow of a fluid. The mass flow rate is delta M over delta T. That is, at a given point, what mass passes this point. So if I imagine a cross section of this pipe, what mass passes that point in a given amount of time? And then the other flow rate is a volume flow rate. We'll talk about the volume flow rate in the class, and you'll have to calculate both of these in the lab. The volume flow rate is a measure of delta V, or the volume, as a function of time. So again, a lot like the mass flow rate, if I imagine a cross section of my pipe, what volume of fluid passes that point in a given amount of time? Usually we'll call this Q, by the way. Q is equal to delta V over delta T. Our units for these are going to be kilograms per second, right? Mass over time, and here it's going to be cubic meters per second. Often when you're working with flow rates, dimensional analysis is your friend, that you can use dimensional analysis to think about what is the flow rate at a particular point. Now, the volume flow rate, because we're dealing with an ideal fluid that is non-viscous, incompressible, steady motion, and irrotational, especially the steady motion, we can say then that in a fluid that travels in a pipe, let me show you an example of a pipe here. Sorry for the interruption. So imagine that I have a pipe that has a cross-sectional area here. I'll call this A1, and then that pipe gets bigger. So this is going to be A2, and A2 is just bigger than A1. Now, because I have this ideal fluid, I know that the flow rate here has to be equal to the flow rate here. Oh, goodness. Okay, sorry about that. So here I have this pipe and it gets bigger. I go from A1 to A2 and A2 is bigger than A1. However, the volume flow rate, Q1, must always equal Q2. The volume flow rate must always be constant. That's true, by the way, for the mass flow rate too. That is, if I have a certain amount of fluid right here, I have to have the same amount of fluid right here. Otherwise, if I have less, that means that somewhere along the way, I'm leaking fluid out of this system. Or if I have more right here, that means that I have fluid being injected into the system. And we're assuming that the system is always closed. So the volume flow rate must always be constant. Also, we assume that because this gas is or this fluid is incompressible. So at no point is the fluid getting compressed into a smaller space or being rarefied over a larger space so that you have a bigger or smaller volume flow rate. So Q is equal to Q1 is equal to Q2. Now remember, Q is equal to delta V divided by delta T. That is the definition of volume flow rate. We can imagine here that this volume is equal to an area times a distance. Right, so if I imagine that I have a cylinder right here, this is some area, this is the distance, or the height of that, or the length of that cylinder, and so it's an area times a distance. And so if I look at this, A times D divided by T, notice that this D over T is our expression for our velocity. So the volume flow rate Q1 is equal to A1 times V1. And so that leads us to an equation called the equation of continuity, or the continuity equation. And the equation of continuity says that A1V1 equals A2 V2, that the area right here times the velocity of my fluid will equal to the area times the velocity of my fluid here. So if I'm looking at a pipe that gets smaller, for example, A1 over here is big, A2 over here is small, what happens to my velocity? Well, if A2 get small, that means that V2 has to get big because this value is always constant. The product of A and V will always be the same. So if I decrease A2, like if it gets a bit smaller as it does here, I start out with a small V and then I get a big V. And in one of the simulations, you'll see how that works out. So that's called the equation of continuity. It's a really important equation. By the way, that comes up if you have, say, an artery. We'll talk about this in the class. If you have an artery, blood is flowing through it, and you get a blockage right here, then here I have a small velocity, v is small, and here I have a big velocity. We'll talk about this in class, but this big velocity right here will actually cause an area of low pressure. That's due to something called the Bernoulli principle. Bernoulli principle is based on the conservation of energy, and one of the results of that is that if V goes up, pressure goes down. It's also the idea behind a wing that I have high velocity air over the top part of the wing, causing a low pressure, and I have a high pressure underneath, and then that results in a lift. The lab doesn't deal with the Bernoulli principle, but we do work with the Bernoulli principle in the class. I'll just sort of introduce it here. That's all for this lab. I'll have another video on how to use the PhET simulation.